Hello student, I am your Kiran Kumar from Nature of Physics. Today topic is Kelvin-Planck statement and Clausius statement from the second law of thermodynamics is the important LAQ for board exam purpose. I am doing this video. Okay, so Kelvin-Planck statement and Clausius statement, heat engine and also refrigerator, clear explanation is there and also useful for objective point of view. Okay student, Kelvin-Planck statement, it is impossible to construct a heat engine which completely convert heat energy supplied to it into useful work. So according to the Kelvin-Planck statement, it is impossible to construct a heat engine in which completely heat energy convert into useful mechanical energy. Best example is bike, in which fuel we are using. So fuel burn with the help of oxygen, so that here heat energy produces, heat energy convert into mechanical energy according to law of conservation of energy. But some of the heat energy transfer from system to surrounding student. That's why it is impossible to construct a heat engine total heat energy convert into useful mechanical energy. Yes, and Clausius statement is second one. So it is impossible for self-acting machine unaided by any external agent to transfer heat energy a body at low temperature to a body at high temperature student. See student, best example here, heat always flow from the higher temperature area to lower temperature area. Heat never flow from the lower temperature area to higher temperature area. If heat is flowing from the lower temperature area to higher temperature area, best example is refrigerator, in which electrical work done on the refrigerator. That's why heat is flowing from the cool area to hot area, that is lower temperature area to high temperature area student. So heat is by external agent only flowing from the lower temperature area to higher temperature area, but heat never flow self from the lower temperature area to higher temperature area. Okay, once again repeating, it is impossible for a self-acting machine unaided by any external agent to transfer heat energy from a body at low temperature to a body at high temperature. Okay, and heat engine, next one is refrigerator. First, heat engine is a device in which heat energy convert into useful work, that is mechanical energy also we can consider. Okay, it consists of following essential parts student. First one is source, second one is sink, and third one is working substance is there. So in the order we can discuss source, working substance and sink student. First discussing about the source. Source is a hot reservoir at a temperature T1 student. Okay, so it is maintained at high temperature T1. Heat is extracted by the working substance. This is the working substance from this body without change its temperature. So there is a transfer of heat from the source to working substance through sink student. Okay, so that substance from this body without change in temperature, the temperature is T1 student, heat observing is writing Q1. Its thermal capacity is infinity student. So source thermal capacity is infinity at high temperature, hot reservoir. Sink also low temperature, cold reservoir student, and also its thermal capacity is infinity for the cold reservoir is sink student. Okay, and the working substance, heat engine working substance is considering here. See student, the working substance for steam generator, steam is the working substance. For diesel engine, the working substance is diesel. Here the working substance, it absorbs a certain amount of heat from the source. So the working substance which absorbs the certain amount of heat Q1 from the source at a temperature T1. Okay, and convert a part of it into useful work student. In this Q1 heat energy, some energy convert into work done. Okay, and remaining energy discussing, that is eject remaining heat to the sink. Remaining heat energy is Q2, which is ejecting to the sink, student. Okay, Q1 heat energy observed from the source and Q2 heat energy ejected to the sink. So there is a work done between the heat difference from the source to sink. Source at a temperature T1, sink at a temperature T2. So there is a work done by the system in the heat engine, work done by the system. That's why arrow mark is up from the working substance, student. So that work done, which is equal to Q1 minus Q2. Okay, and next sink already discussed in slowly. Again once I will read. It is maintained at low temperature, that is T2. It observes the heat ejected by the working substance. Whatever amount of heat is ejected by the working substance, it is observed by the sink. That amount of heat is taken Q2, student, without any change in the temperature. Temperature is always remains constant because of here thermal capacity of source is infinity and thermal capacity of sink also infinity, student. Maintain at constant temperature. Source is T1 high temperature, sink is low temperature T2, student. The work done by the system, W is equal to Q1 minus Q2, already I gave you proof. And the efficiency of heat engine, neta, which is equal to W by Q1, it is the ratio of work done to the Q1 heat energy observed by the working substance from the source. Neta, which is equal to W value is replacing Q1 minus Q2 whole divided by Q1. Q1 by Q1 is 1 and minus Q2 divided by Q1 written clearly here. Neta is equal 1 minus Q2 divided by Q1, and also efficiency we can write in the form of temperature, that is neta, which is equal 1 minus here Q2 is there, that's why T2 temperature divided by T1 temperature. So this equation represents with respect to heat, this equation represents temperature, student. So heat and temperature clearly represented in the diagram. Next I am discussing about the refrigerator. Refrigerator is an ideal heat engine. What is refrigerator, student? Ideal heat engine working in a reverse direction. Clearly different colors written. Working in what direction? Reverse direction comparing to the heat engine. Hence it is also called heat pump. Hence it is also called heat pump. So clearly we can compare with this heat engine, student. In the heat engine, okay, Q1 heat energy observed from the source and Q2 heat energy ejected to the sink. Here quite opposite, student. Here Q2 heat energy observed from the sink and Q1 heat energy is ejected to the source. Okay, and detailed continuation we will discuss. Notice that here arrow mark also, see, work done by the system, work done by the system, arrow mark is up in the heat engine, but in the refrigerator work done on the system, student, work done on the system. Example, refrigerator, that is electrical work done on the refrigerator, that's why heat is flowing from the lower temperature area to higher temperature surrounding. Okay, so refrigerator is an ideal heat engine working in a reverse direction, hence it is called heat pump, student. In a refrigerator, the working substance extract an amount of heat Q2 from the cold reservoir at low temperature, already represented. Here sink already detailedly discussed in the heat engine, again I don't want to discuss. So sink at low temperature, that is cold reservoir, its temperature is T2, student. Here from this Q2 heat energy observed by the working substance, okay, and clearly written here. Okay, and next one, an amount of external work done W on the substance. So an amount of external work done W on the working substance, student. Okay, see there, an amount of external work done W on the working substance is there, on which work done W, then only heat is flowing from the lower temperature area sink to the higher temperature source, student. Okay, and finally an amount of heat Q1 heat energy is ejected to the hot reservoir, quite opposite direction from the heat engine. In the heat engine, heat is flowing from higher temperature area to lower temperature area, so work done by the system. Here heat is flowing from the lower temperature area to higher temperature area by the external work done. Notice that difference. Okay, say student, so source is at a temperature T1. Okay, and the ratio of heat extracted Q2 from the cold reservoir to the work done W on the working substance, already we did, on the working substance is known as beta. Beta represent coefficient of performance. Okay, so that beta is the coefficient of performance, which is equal to Q2 divided by W. It is the ratio of heat extracted from the cold reservoir to the work done on the working substance is known as beta is the coefficient of performance. Again repeated, beta is equal to Q2 divided by W, but work done on the system, that is Q1 minus Q2, student. Okay, W is equal Q2 divided by, instead of W I am writing here Q1 minus Q2, student. And then continuation we can write beta, which is equal to T2 divided by T1 minus T2. Same only here, this formula with respect to heat, this formula with respect to temperature, already relatedly we did, student. Okay, and next there is a relation, the relation neta, which is equal to, it is useful for only objective point of view, so for IP no need to write. So neta, which is equal to 1 divided by 1 plus beta, and beta, which is equal to 1 minus neta divided by neta. Note represent the relation between the neta and beta. Neta represent the coefficient of heat engine, student, and beta represent the coefficient of performance. So relation is clearly represented. Please do like and subscribe our channel Nature of Physics.